Hello class, welcome to another video. Today we're going to learn about conservation of energy. Now as soon as I finish eating this food, rice, hot sauce, and meatballs, yummy, my favorite, we'll get started. Alright, now that I fill my stomach with food, I have a cup of coffee, my favorite form of liquid energy. Sort of. Caffeine's not really energy, it's a stimulant. Anyways, here we have a simulation, one of my favorites. Some of you might have played it with this before, but it's the PhET simulation for Energy Skate Park. Now this Energy Skate Park does a great job of showing the relationship of conservation of energy. Okay, so you should all know by now that conservation of energy states that energy cannot be created nor destroyed. Okay, you can't create energy, you can't destroy energy. The energy you start off with is the energy you end up with. So I'm going to introduce a couple of vocabulary terms that you should definitely write down when I introduce them. Okay, the first thing I'm going to show you is the energy bar graph. Now on the right here where we have total energy, okay, another way of saying total energy is mechanical energy. Okay, the amount of mechanical energy this guy has is constant. Okay, that's the total amount that he will have. And another vocabulary term here is what we call a system. Okay, the system is the scenario that we are looking at. We can change the system by changing the guy that's on the skateboard, like making it heavier, or raising the skate park up and down. Okay, but the system is the thing in focus. Okay, so when I mention system or mechanical energy, know that mechanical energy is the total amount of energy, and system is the scenario that we are currently focusing on. Alright, so here at the bar graph, we can see that as the guy reaches the max height, look at this potential energy bar. Okay, it's big, it's really big, but then as he goes down, I'm going to put this in slower motion, look what happens to the potential energy. It turns into kinetic energy and then back into potential. And here's the reason why. When this man is at the peak, he only has potential energy, and that's because kinetic energy, the word kinetic means motion. Alright? Now, at the peak, he is not moving. There is zero motion, zero velocity. So he has zero kinetic energy. But as gravity, does work, and gravity pulls him down, okay? Gravity works on the system, pulls him down, it's going to give him, it's going to transfer some of that potential energy into kinetic energy. Notice that at the bottom, at the lowest point, he has the greatest amount of kinetic energy, and it quickly transfers into potential energy. Alright? If I want to change the amount of total energy or mechanical energy, I have to do work on the system. Okay, I'm going to do that by raising the skate park. Alright? Now think about this. If I work on the system, I am putting in energy. So if I put in energy, the mechanical energy should increase, like so. Look at that yellow bar. Look how it's increasing. Okay. Now, if I do negative work, if I bring the skate park down, I'm doing negative work. Therefore, I take away some of that energy. All right? Because work and energy, they go hand in hand. They go simultaneously hand in hand. They're proportional. The more work you put into a system, the greater the energy. However, what is not proportional is the relationship between kinetic energy and potential energy. They are inversely proportional. Means if kinetic energy goes up, potential energy must come down. Okay? A good way to look at that is another type of graph. Here we have a position versus energy graph. Alright, so in this position versus energy graph, we can clearly see that as the kinetic energy, which is represented in green, goes up, the potential energy, which is represented in blue, goes down. Notice that the total energy, aka the mechanical energy, stays the same. Okay? And the only way that that line can change is if I do work. Once again, I'm going to do work on the system. I'm going to do positive work. I'm going to increase the amount of energy. And notice how everything shifts accordingly. Okay? If I do negative work, we can expect that the kinetic energy and the potential energy should also be affected. Just like that. Okay? Now, if I were to change the skate park itself, we can get a clear representation of the inverse proportional relationship between kinetic energy and potential energy. Alright? So let's clear this. I'm going to push play. Now, we have a guy at the highest point along this ramp. So when he's at the highest point, he has the greatest amount of potential energy. And we can expect that as he goes down the ramp, all that potential energy will turn into kinetic energy. So remember, they are inversely proportional. As one goes down, the other must go up. So let's see if that is true. Wow, would you look at that? It's like I know a thing or two. Okay. Another way to look at these graphs is between a displacement versus time graph and a velocity versus time graph. Okay, now at first this might be a lot of information, but if we actually slow it down, take the time to look at it, it's pretty simple. Let's take a look at the displacement versus time graph first, which we all know that the slope for a displacement versus time graph is the velocity, because distance over time, meters per second, velocity. Okay, so if we take a look here, the displacement at this point, at time is 0, is up there. It's in fact the highest point. So at the highest point, we can expect and assume that it has the greatest potential energy. If it has the greatest potential energy, the kinetic energy, assuming that it's moving from rest, will be 0, where the velocity will be 0, because the two go hand in hand. So if we take a look here, well, would you look at that? At the highest point, the velocity for the energy skate park was 0. And as the guy went down the incline, okay, as the guy went down the ramp or went down the incline, his velocity increased. And that proves to be true right here. Now, if you're thinking to yourself, wait a minute, Shirley, it's going from 0 to a negative number. Isn't technically that a decrease? To which I would reply, well, normally yes, but remember in physics, positives and negatives just represent direction. Okay, so the real reason why that this velocity graph is in the negatives is because if we take a look here, for the displacement versus time graph, the slope is negative. And if the slope is negative for a displacement versus time graph, the velocity is also negative, which we see down here. So as the skateboarder is going down the ramp, his velocity is increasing. And we can clearly see that in this part of the graph. Okay? The velocity is increasing. The magnitude, the number itself is increasing until we get to right here. It looks like the highest velocity. And we should know that at the highest velocity, the object has the lowest height or the lowest potential energy. And we can see that here. Okay? When it's at its greatest velocity, it's at its lowest point. And then the guy goes back up the other side. Right? Because the displacement increases. Now, it increases negatively, but still increases. And so we can assume that as he's going up the ramp, he is slowing down. And we see that here. As he goes up the ramp, he slows down until he reaches a velocity of 0. And at that point, he should be at its highest point. Highest point, right there. Okay, so I hope you enjoyed this video and you'll have a better understanding of how conservation of energy can be represented through graphs. Thank you.